So in the correlation table that we just made, looking how all the different variables relate to each other, how are we going to interpret them? There's several things that we need to pay attention to. First of all, we need to pay attention to its direction. Is it positive or negative? In fact, that's kind of the most important thing. Is there a positive relationship or a negative relationship between the relationship? So that's the first thing that we want to use to describe a correlation. And secondly, its strength. Now here's some guidelines to help you interpret how strong of a relationship is. From 0.5 to 0.10, that's considered a strong relationship. They're pretty closely together. From 0.3 to 0.5, that'd be moderate. And in psychology, it's pretty rare to get strong correlations, and it's not too common to get moderate relationships, but it's fairly common to get weak relationships between 0.1 and 0.3. Or sometimes I prefer to say between 0.15 and 0.13, because below 0.15, it's pretty weak or no relationship at all. You can't really tell from one variable how that it would be influenced by another when it's that weak. Now, you might a general rule in psychology is that whenever we have variables that are very strongly related to each other, the absolute value of r is greater than 0.7, so like if something was like minus 0.8 or plus 0.8, the two variables might be measuring the same thing. It's like if we were measuring extroversion and talkativeness and they came out really strongly correlated, then we might say, ooh, I wonder if those two things are the same thing. Or if the absolute value is high, but it's like close to minus 0.1, they might be the opposites. Like, ooh, here's one measure for introversion, here's one measure for extroversion. They're correlated at minus 0.95. It's because they're measuring the same personality trait. One is just the inverse of the other. Now, an important statistic is R squared. And so basically you just take r and you times it by itself, and r squared is the fraction of total variability in the y variables that's accounted for by the x variables. For example, the correlation in men between height and shoe size is 0.95. So if we were to square 0.95, type into the calculator 0.95 times 0.95, we'd get an r squared of 0.90. So that means that 90% of the variability in a sample of shoe sizes is accounted for by the variability in height. And that means there's 10% that's predicted by other things that are accounted for by other factors. Perhaps your family has small feet. That would influence the correlation. Maybe you're dressing like a clown, or some people are dressing like a clown on the day that everybody makes the measurements. And the clowns are going to have really long feet. Maybe you forgot your shoe size. There's all kinds of things that would account for it being an imperfect relationship, and r squared shows what percentage of the variability can be accounted for by other factors. Now, an important concept to remember with correlation is that it's called the effective range on correlation. If x and y are correlated variables, but we only look at a small range of x or a small range of y, then we're not going to see the correlation very well. Let's take, for example, the correlation between SAT scores and grade point average. Now, in most schools, there's almost no relationship between SAT scores and grade point average, and that's because most people go to schools that have a narrow range of SAT scores. Some people go to schools where everybody has high SAT scores. Others go to schools that have a medium SAT scores. Others go where they have low SAT scores. However, in other schools where they get a whole range of SAT scores, we're going to see the correlation between SAT scores and GPA. So looking at these 9 scores, there's a clear relationship, but if we just looked at the high scores, it looked like there'd be a negative relationship between GPA and SAT scores, and these other two don't look like there'd be much of a relationship at all. So if we don't get the whole range of a variable, for example, if we're studying leadership and what leaders do, and we only measure really strong leaders, we're not going to get much of a correlation between anything. We need to measure both good leaders and bad leaders to be able to see what's really different in their behavior between the two. Now let's look at the effect of extreme scores on R. Let's take, for example, this study of the number of Star Wars toys in people's bedrooms. And here in this first section over here, we have 5 sample points, and we've got boys between the ages of 10 and 15. So teens and preteens, and we've got their age and the number of Star Wars toys that they have. So it goes from like about 9 to about 14. We calculate the correlation, and it's really weak, R of 0.11. And you look at that, that doesn't look like much of a line there. However, if we put one extra data point in up here, where we have a 30-year-old who has 30 Star Wars toys, and we recalculate the correlation, we get a correlation of 0.94, an extremely strong correlation. And that's because this outlier is throwing everything out. So it's important to check our data to make sure that we don't have any outliers, because outliers basically don't belong in the data set. And so we're studying teens and preteens, but we throw in this 30-year-old guy that has a bedroom full of Star Wars toys, and the formula that we're using to calculate R goes haywire and says that there's a really strong relationship. So basically the kind of test is that both X, like the age, and Y, the number of toys, should be normally distributed for R to be meaningful. And one of the ways that we could do that is to calculate the Z for each score and see if we have any extreme scores. This one might be a Z of -4 or so, and that's too low. That's a sign that it's an outlier and doesn't belong in the study and should be thrown away. Now, one last concept, and notice how we've got a red flashing light here. That's because this is really important. Correlation does not imply causation. Now, what does that mean? Let's take an example of something that I hear about in the news every few years. Somebody does some study, and there's a positive correlation between the number of diet soft drinks that people drink and their weight. And it's always the same direction. The more diet soft drinks that people drink, the heavier they are. Now, there are 4 possible causal explanations of a correlation. These are really important. These are worth memorizing. First of all, maybe it's diet soft drinks that cause people to put on weight. And that's the idea that A causes B. And that's usually what the media is saying, that, aha, since there's correlation, diet drinks cause people to put on weight. Therefore, you shouldn't drink that, go and drink the sugary stuff. Aha. Well, that's just one of 4 ways to interpret correlation. Maybe being heavy causes you to drink diet soft drinks. Oh, maybe people that are skinny, they don't bother drinking diet soft drinks because they tend not to put on weight. But maybe those people that are heavy, they say, ooh, I don't want to get even more sugar, I better cut back and drink the diet soft drinks. A third possibility is that there's a third variable that causes both weight gain and the consumption of diet soft drinks. For example, a sweet tooth. Maybe some people just really like sugary stuff, and they want to eat cookies all the time and cake, and oh man, I love this stuff. Wait, no, let's get back. So it might cause them to like really sweet stuff, and which causes them to put on weight, but they like diet soft drinks because it's sweet too, so they drink a lot of that too. So that would be a third variable causes both A and B. And then the fourth interpretation is that the correlation is spurious. That means it doesn't really exist in the population, and it just resulted from measurement error or chance. If we were to do another sample, we'd get another correlation. It might be a negative correlation. So anytime that we have a correlation, we cannot say, aha, A causes B or B causes A. We have to say that, well, maybe A causes B or maybe B causes A. Maybe a third variable causes them both, or maybe the correlation is spurious.